transfer that data from the satellite to the actual readable or understandable form?
Data comes onto what we call as Indian Deep Space Network, which is IDSN in Bangalore. We have a huge antenna of 32-meter, through which the communication happens with the satellite. And the data comes to our payload operations center, which is, for example, in SPL, when I was there, it was in Trivandrum, or in PRL, when I'm here, it is in Ahmedabad. So the data comes to us after a lot of processing at the station from where the data is collected. And then we start looking at it. And we draw certain basic parameters to understand whether voltages are okay, temperatures are okay, commands are going properly, and the data has been collected. And data is integrated. Means there is no break in the data. There is no abrupt breaks in the data set, which reflects that maybe instrument is not working well. So everything integrity is checked. And once it is checked, then we started looking at the what is the science.
Hello everyone, welcome to Space Science Podcast Series 8, and I am Prachi Verma, and I am on a mission to connect space enthusiasts and youths with all the scientists, founders, researchers out there for a better, broader perspective in space science sector and the opportunities lying in this field, so that we can actually take that for our career as well. So, without any further delay, today I would like to welcome our guest with that motive that will get inspired by him. And today's guest is none other than Director of Physical Research Laboratory, that is PRL, which is a department of space under the government of India. Also, he is the recipient of Shanti Swarup Bhatnagar Award, which is known as India's most prestigious science award and Infosys Prize. Also, he is the board of trustee of International Academy of Astronautics. So let's welcome today's guest, who is Professor Anil Bhardwaj sir on this podcast. And without wasting any further time, let's dive into a deep conversation with him. So, how do you feel to connect to our listener today through this podcast, sir?
Oh, feeling great, Prachi. And thanks for inviting me on this podcast, which I hope will inspire many more to join the area of space exploration and planetary science.
Yes, sir. Of course, of course. As I already mentioned PRL, and I have a lot of question going on in my mind while I study that it deals with research and stuffs. And when as a student, what we debate upon is that whether should we go for research or whether should we go for engineering. So what actually inspired you that you choose the planetary science as your journey, which was quite a niche area at that time, but while it's still in progress this time, in this moments as well. But why did you actually choose it at that time? What actually inspired you?
Okay, so you want me to go back into my
Yes.
childhood days when I used to get inspired by looking at, the black spots on the moon and looking at the sky and trying to identify. Uh, so once in lifetime you can see Comet Halley.
Yes.
And that visit was inspiring me to understand why these objects go around the sun. They visit for after such a long time, and what are they made up of? And that was also a period when Voyager 2, which is a spacecraft from NASA, going or passing by the planet Uranus. So these are certain, events which happens in one's lifetime, which depending upon your interest, you pick up them and try to understand how things are happening. And these things actually inspire me to start thinking about working in the area of planetary science. And I was lucky that I got a good mentor to start with to look into those aspects and try to understand what processes actually takes place inside those bodies and trying to understand those phenomena which takes place. And that's how the journey of planetary science started.
Okay, sir. So, like, as I asked the research domain, so did you believe that you will have reached to this point till now or till in your future? Like, you will become the director with this domain itself, research?
No, see, these things evolve as you grow and you work. Nobody can think about, oh, I will become director, so I should take this area or this field. It's all is a passion. So if you have a passion, if you have a deep interest, you have this fire inside to keep working, getting motivated, whether it is happening or not happening in terms of research. But you know that yes, there is something new which is there for you to do. That is the most important thing rather than putting a goal in front of you. And that is how my journey has evolved, both as a student and then as a scientist.
That's so great to hear from you, sir. The journey from SPL to directly to PRL, it has been a very long process. But I would like to ask a question upon this as well. So, while you were working as an ISRO scientist at SPL, that is Space Physics Laboratory, and then coming to PRL, I believe that would have changed not only as a person, but your mindset would have changed a broader perspective upon how the space looks or how the universe actually functions. So, how did your mindset change as a person as well as a scientist as well?
Uh, I actually started my career as a theoretical uh, modeler, I should say, or a simulation activities, theoretically understanding the phenomena or processes which happens in atmospheres of different planets. So I did my research, or I should say PhD, in outer planets, that is Jupiter, Saturn, Uranus, Neptune, and on comets. And my focus was to understand the processes of formation of emissions from these atmospheres. And it's a process where the sunlight and the charged particle interacts with the atmosphere of any body. For example, in the case of Earth, we talk about aurora, right? And we talk about aurora happening in higher latitudes in the polar regions of the Earth. And they happen when there is a charged particles coming from the sun interacting with the Earth's atmosphere, and you say there is a storm, magnetic storms, and therefore there's aurora formation. Same way, in the Earth's atmosphere, there's a phenomena called day glow, which is a glow of the atmosphere, which is happening because of the interaction of solar electromagnetic radiation, largely the ultraviolet and EUVs and X-rays, and which produces emissions of this atmospheric species like Earth's, in the case of Earth, it is oxygen, nitrogen emissions. So I was looking at what happens in the case of different planets. For example, outer planets which are dominated by hydrogen and helium, H2, H, and He. And in the case of comet, it is largely very small bodies, but they are dominated by water vapor, H2O. So how these emissions are getting produced, what kind of chemistry takes place. And when I talk about this phenomena, I'm talking about with reference to the Earth, it's something like 100 kilometers above the surface of Earth, going to somewhere around 400, 500,000 kilometers above the surface of the Earth, where it's almost like a vacuum, but it's not vacuum, there's atmosphere, and that's why this all phenomena takes place. So my interest was from understanding them from theoretical perspective, putting into equations, writing codes. So I used to run Monte Carlo models, I used to write codes. And my research, if I don't know you will be aware or not, I did my research by punching cards, you
Yes.
know.
Yeah.
So there used to be a card, and we used to punch the code on that, and then there'll be a huge stack of those cards, and that I will give it to the computer operator, and he will put it that, and then my code will run. And in case there is a small typo error in one of the cards, the whole program will not work, and there'll say error in compiling, and then I will generally give it in the morning. This is my days in BHU at IIT BHU, and in the evening, we'll go and see what output has come out, and that fellow will tell, sir, आपका ये card खराब है, फिर से replace कर. So it was a very different environment of research compared to now, where you have very fast computers and PCs, personal computers on which you can run those codes. But at that point of time, there was no PCs even. PCs, or I should say 286 and 386, they were the first initial PCs which came at the fag end of my own research, PhD days. So the type of learning which you have for your research and passion has to continue. Otherwise, you will not find that it's very charming that you wait for the whole day for output to come, and the evening you say, oh my God, one typo error has happened. But that was also interesting because we used to get a lot of time to study and to read. And I used to go to library in Banaras University, the BHU, and there's a lot of books, a lot of journals we could read and understand what's happening currently in the field, and how I had to tune my research and to see something different which I can do. But after I joined Space Physics Laboratory in Vikram Sarabhai Space Center as a scientist after my PhD, I had an option to go abroad, but then I preferred that I should be in India and continuing to work. And therefore, I joined as a scientist there. And then I found that not many people are working in planetary science at that point of time. I'm talking about early 90s. And but still my passion was there to continue in planetary science, and I started looking at the other options. So I started looking at observations using telescopes, both ground-based and space-based. And that motivated me to look at Hubble Space Telescope, which is a UV telescope in space, looking at Chandra X-ray telescope, which is an X-ray telescope in space, XMM Newton, and things like that. And therefore, I started making observations. So from theoretical modeling, I started making observations using this big high-end telescopes in space. And then I also started looking at the giant meter wave radio telescope in Pune, which is one of the biggest in the world. How I can link different emissions from radio to X-rays to ultraviolet. Still looking at planet Jupiter, for example, and how I can, club these observations and then put into modeling, which was my domain of research. Around late 90s, or you can say in the new millennium, when India started talking about having a mission to moon, and earlier itself, around 96, 97 time frame, I was also working on whether I can propose an instrument to fly on Indian satellites or even in International Space Station. But it was not getting certified because not much was happening within the country with respect to this kind of activities. But when the Chandrayaan-1 mission opportunity came, and I said, no, I will propose a mission. I will propose an instrument to fly on that. And I joined collaboration with the European scientists to propose an instrument which is called SARA. SARA means not SARA, but SARA means Sub-KV Reflecting Analyzer. Okay. And this instrument was selected to fly on the Chandrayaan-1 mission. And that's how my journey on exploration of Moon, Mars, and different objects in the solar system started with Indian missions, Chandrayaan. Subsequent to that, we had experiment called MENCA on the Mars orbiter mission, where I was the PI. And MENCA is not, the Menka of Rishi Vishwamitra, but Menka stands for Mars Exospheric Neutral Composition Analyzer. So this was again a very unique instrument where we are interested to study the upper atmosphere and exosphere of Mars and what is its constituent and how does it vary as a function of altitude, latitude, longitude, diurnal variabilities, because Mars has roughly uh, the same length of day as Earth.
Mm.
So it is slightly more than 24 hours, which we call as not day but sol in for differentiating with Earth's day. And that was an instrument which was very successful. And as you must be knowing that Mars orbiter mission of India made India the first country in the world to have the successful insertion of a orbiter around the Mars in the first attempt. So that was a very unique, both in terms of the technology feat which the country got, but also that we could operate this mission for more than 8 years, though the lifetime was only 6 months. So, it surpassed its
Yes.
lifetime for almost like factor of 10 and things like that. So that was a very good experience for me to take part in the first Indian Mars orbiter mission, Mars mission. And then around the same time, we are talking about second mission to Moon, the Chandrayaan-1 mission. So I was proposing a similar instrument which we have flown on Mars, Menka. So it's a brother called Chase, which is Chandra's atmospheric composition analyzer, which is again a mass spectrometer, which was flown in 2019 on the Chandrayaan-2 orbiter, and it is still operating around the moon and providing us excellent quality of data. But around the same time frame of around 2014, 2015 time frame, we are also working on the Chandrayaan-3 mission, which is a lander mission after the setback from the Chandrayaan-2 lander mission. And we worked for the Chandrayaan-3 lander, where PRL had an instrument called APXS, Alpha Particle X instrument, on the rover of the Chandrayaan-3, as well as for the Chandrayaan-2, and an instrument on the lander called Chasti, which is a very, very unique instrument to go inside the surface of the moon to measure the temperatures up to a depth of 10 centimeter. Almost like every 1 centimeter, we are getting the data. And this was the first of its kind in the world to make measurements of the top regolith, we call as a soil as a regolith on the moon. And that all has given very unique science. So my journey from SPL, moving from theoretical modeling to observations to instrumentation development activities, and growing to become a director of a specific laboratory, and then given chance to move out from SPL to take a bigger responsibility of directorship of PRL, has been a very enriching experience for me, because the domain of research activities at SPL and in PRL is much more wide at PRL, and therefore it becomes good for you to understand what's happening in other fields and how progress is happening and how I can take knowledge from them and apply into my field. So it becomes very important for us as we grow up to grow and become wider in terms of your knowledge.
That's your story is not only inspiring, sir, but it was so interesting to listen from you. I was like continuously listening. How did the punch code happen? Then you started with the journey from Chandrayaan, Mangalyaan, all these stuff. Sorry, yeah, Mangalyaan. So it was so interesting to hear this from you. And as you said, the discoveries and research which you do at PRL, and after that, that is what the ordinary people are also reading through books, through all the social medias. But I would like to know, once the rocket reaches to the space, then it goes and collects the data. What actually, of course, you can't say the fully what actually happens there, but what is the thing that ordinary people should know? How do you transfer that data from the satellite to the actual readable or understandable form?
Okay, so let me give you a little background so that you appreciate and understand it better. So the rocket is actually a vehicle which takes the satellite into space. Okay. Now the satellite itself has to function. And for example, I will take the example of Chandrayaan-1 because that is the first Indian moon mission as well as the first Indian planetary mission. So we had a PSLV, the Polar Satellite Launch Vehicle, in its XL form, which is like little bigger form of a PSLV, and we used it to push the rocket into space and orbit around the Earth. Then the satellite itself has its own propulsion system, which takes it from Earth to Moon. Okay, and then you have to get inserted into an orbit of a body. So
Yeah.
it's a very complex process where you reduce the velocity so that the spacecraft feels the gravity of a planet or an object, and then get inserted into it and then start going around it. So from Earth orbiting, it goes to a transfer orbit, then get captured into the planet's gravity, and that goes around it. And then you make it perfect into an orbit which you require for making observations. In the case of Chandrayaan 1, for example, it was 100 kilometers circular polar orbit. Okay. Now, once you have done this all, you start operating on instruments. And for example, in the case of Chandrayaan 1, we had an instrument called SARA, which is sub-KV time reflecting analyzer. It has two different sensors. One was looking at the solar wind, which is coming from the sun. The other one was looking at the impact of the solar wind on the surface of the moon and look at the ENA protection. Now, so this is like a sequence of events which happens on the spacecraft where you first commission the payload. Commissioning means you start giving, you make it on, you give some kind of command from the Earth to make it operational and see what is happening, whether my instrument is working properly. If everything is looking fine, then we go into phase of actual observation. So it's a sequence of commands given from the Earth. It takes a couple of days to weeks, sometimes months, for it to start making it operational and collecting scientific data. Once all this is done, the data is coming back to Earth. So communication is happening radio waves.
Yes.
So you understand. So these we call as S-band or X-band or Ka-band propagation and data. In addition to data, we also get health parameter of my own payload and this whole spacecraft.
Okay.
Because everything should work perfectly well, and then only you will get good scientific data.
Yes.
So as the data comes onto what we call as Indian Deep Space Network, which is IDSN in Bangalore, we have a huge antenna of 32 meter, through which the communication happens with the satellite. And the data comes to our payload operation center, which is, for example, in SPL, when I was there, it was in Trivandrum, or in PRL, when I'm here, it is in Ahmedabad. So the data comes to us after a lot of processing at the station from where the data is collected. And then we start looking at it. And we draw certain basic parameters to understand whether voltages are okay, temperatures are okay, commands are going properly, and the data has been collected. And data is integral, means there is no break in the data. There is no abrupt breaks in the data set, which reflects that maybe instrument is not working well. So everything integrity is checked. And once it is checked, then we started looking at what is the science? What is the data telling? So we plots, there are different kind of plots we make. First of all, to know where my instrument was looking, where it was in space, what was the field of view of the instrument, right? So then there is a lot of algorithms we have to run to understand, because in space there is no reference, right? So you have to take the reference of heliosphere, where was the sun, where was the earth, where was the moon, and where was the spacecraft around the moon, because that also matters. What latitude, what longitude, what solar zenith angle, what sun earth angle, what spacecraft to moon to earth angle. So there are a lot of parameters which are there. And after all this, we see something, and then we started looking at what science it is coming. So there's a lot of activity which keeps happening at the background. where a lot of people start looking at this data. The instrument engineers will be looking at whether my instrument is working fine. So they look at all the parameters of voltage, temperatures, currents, operating conditions, the spacecraft conditions, and things like that. Once the data start coming down, we start looking at it, what we are seeing, and then we start interpreting. So in the case of Chandrayaan 1, we were very excited to see that we are seeing ENAs, which is the first observation of its kind on the moon, where we have seen energetic neutral atoms getting reflected back or scattered back from the lunar surface. Because moon doesn't have an atmosphere. Yes. Right? It doesn't have a global magnetic field like Earth. So it lacks both of this, and therefore the solar wind directly comes and hits the lunar surface. Solar wind is a plasma coming from the sun with a speed of something like 400 kilometers per second. So it's a supersonic, super alphanic plasma. And it comes and hits the lunar surface, and we are all thinking that it is completely absorbed. And on the day side, that is the side which is seeing the sun, and there's not much happening. And there's a long plasma wake or vacuum being created on the night side. But this SARA instrument has completely changed our understanding with respect to how the solar wind actually interacts with the lunar surface. And we found that almost like 20% of the impacting solar wind protons, because solar wind consists of protons and WN is helium. Protons means H plus, one electron taken out from hydrogen. So you can assume a proton coming with a speed of 400 kilometers per second. You translate it into energy, it is something like 800 to 1 keV proton coming and hitting the lunar surface. And almost like 20%. So 1 in 5 particles are reflected back, scattered back in space. And that is what my instrument was measuring actually. And that gave us a lot of new plasma physics, surface plasma interactions, processes of energy loss, inelastic scatterings on the surface. So it was a totally new field for a lot of people around the globe to say that what is happening on the lunar surface, why it is getting reflected back. We should not see reflected or scattered protons on the surface. So these kind of, new science comes out when we look at the data and then try to interpret it and explain what is actually happening. So there's a series of activities which keeps happening as the data comes back. But remember that for developing instrument and then calibrating, qualifying, and flying means integrating on the spacecraft, then the spacecraft sits on the rocket, then rocket goes up, then the spacecraft is separated out, then it goes to planet, then it goes into orbit, then we start commissioning the instrument, then data start coming, then interpretation, and then publication. It's a huge lifetime of 5 to 10 years when we see the first light from the instrument and start doing science. So you have to have a lot of understanding, right from instrumentation development to science, and passion and dedication. Because you have to continuously keep working for several and several years before you will see the science develop.
That's so powerful, sir, how the data is actually transformed. And what I noticed over here, that what we used to believe is somewhat is changed while we are doing the research, or while the scientists are actually looking, as you said, the understanding of moon changed. So that's is quite different, and quite things like when we print the book, we print it like that, and after that we have to change it again because our understanding is changing. So that's so interesting to hear as well. But I would like to go up with my last question due to time constraints. So as we are talking a lot about planetary science, and a lot of people are interested in this field as well, but the only thing over here, as I would say, is that students hesitate to take this platform, thinking that what are the opportunities available in this field, how will I go and get the success in this field according to them, whatever the success is. So what are the opportunities PRL offers, as well as the experience that students should take from PRL, that they can help that will actually help them to get success in their career?
Okay, so that's a very good question because that will motivate a lot of scientists and understand how one can take opportunities in this exploration program. India, as you know, has started planetary exploration in the new millennium, starting from Chandrayaan 1. So you can say around 2000 onwards. We had the first mission in 2008, Chandrayaan 1, then 2014, the Mangalyaan, then 2019, the Chandrayaan 2, then 2023, the Chandrayaan 3, and of course, the Aditya L1 mission, which is now in orbit around L1. So, what you need is two things. One, anything where any field, any subject which is exciting, take that and make it as a passion. Whether it is a physics, whether it is chemistry, whether it is a mathematics, whether it is an engineering subject like mechanical, electrical, your own subject, EC, aerospace, aerodynamics, thermal, propulsion, civil, electronics, computer science, name any subject, material science, metallurgy, any subject, because in the space, we need people from all possible branches of science and technology and engineering. And now with the Gaganyaan, that is a human in space program, we have biologists, we have medical science people working in space. So it it is not that you have to study X, Y, or Z subject. No, any subject. Astrochemistry, for example, astrobiology, biogeosciences, biochemistry, biophysics, right? Any subject. Second is you should excel. Excel means you should have a very good understanding of basics of your own subject where you are interested. Third is you have to see how it can be applicable into space. Because once the humans are going to space or space program is expanding, we need young scientists, young blood to take up the domain of research, the domain of technology, the domain of engineering, right?
Yes.
And the second most important is your passion should continue, sustain. It's not that you have a passion to do space work in space or in ISRO or many startup which is coming in the country, but it should get sustained. It takes long time. As I was telling, it takes 5 to 10 years for you to see your instrument working in space and giving you some data.
Yes.
So if you're a short-tempered fellow looking for very short goals, or within 1 or 2 years of working, I should get some fame. It doesn't happen that. You have to work for years. Sometimes it takes 15 years or 20 years. For example, a mission going to Mars, it was a 10-month journey itself for the satellite to reach the planet. And we were working from 5 years behind that. So it is like a 10-year program.
Correct.
So your maintenance of your passion for a long dedication should continue. That is most important. It is not that you have to run behind success. You have to run behind your passion. That is most important. And do with your best ability and capability. That is also very important. A lot of people say, no, isme thoda kam. I should not speak Hindi, but people think about, that इसमें थोड़ा कम ध्यान देते हैं, इसमें ज्यादा ध्यान देते हैं. Like, people try to divert their own mind. That means they are not still clear about what they are actually working at. So that should not happen. There should not be any ambiguity. Whatever it is, it will lead you to something very new, very different. It is for sure. But if you leave that and start jumping around, oh, my peers are doing this, my colleagues are doing this, my seniors are doing this, so I should also do that. It doesn't apply that. Because every human being is very unique. Every human being's thought process, the capabilities, his or her knowledge with respect to as the child grows up is different, right? And therefore, don't compare yourself to others. You should compare to yourself and say, when others can do it, I can also do it.
Correct.
That should be the thought process, right? So that is why, and now as the country is growing, and a lot of new programs are coming up. We are talking about Chandrayaan 4, Chandrayaan 5, and then series of missions, Chandrayaan 6, 7, 8, and human going to moon. there's a large opportunity for youngsters to take part in this kind of programs. And we are talking about the Venus mission, we are talking about Mars lander missions in the future. And therefore, I think it's a very good time for all the youngsters who are interested to take planetary exploration and planetary science to work in this domain and take the country forward.
Yes, sir. Just a second. Am I audible?
I think it is all stagnated or what?
Yeah. Now it's perfect.
Okay.
Yes.
So in between, I think there are some frozen
Yeah.
things.
But audio was audible. So
Okay.
as you said, sir, one thing I could remember from this: don't run behind success, run behind passion. I remember from Three Idiots movie, they used to say, don't success के पीछे मत भागो, वो खुद चल के आएगा. And that's so
Right.
inspiring, sir. So I am
Right.
sure that youth will take up the opportunities and follow the path you set. And I believe that whatever you said completely aligns with what actually happens in youth's life. They keep on switching for a better life and better success. But ultimately, a long term, if you stick to the thing, as you said, is very important. So I'm so grateful to have you on this podcast today, sir. And of course, my podcast was such like you made the podcast even more brighter today. So thank you so much for connecting with us, and hope so our listeners would love watching this and get motivated by this podcast as well. Thank you so much, sir.
Thank you, Prachi, for bringing me on this podcast, which you have been doing. And I hope it will be good for you to continue doing this as well as excelling in studies. Thank you.
Thank you so much, sir.
Thank you. Thank you. Take care. Bye bye.
Bye bye, sir. Thank you.
Thank you.